Dear students, today we discuss a widely used methodology procedure in econometrics, namely Granger causality test. To introduce Granger causality test, remember that although regression analysis deals with the dependence of one variable on one or more other variables, it does not necessarily imply causation. In other words, existence of a relationship between variables does not prove causality or direction of influence. As we have discussed in the beginning, our idea about causality must come from outside econometrics. It must come from economic theory. Theory must say which variable is the cause and which variable is the effect. So regression analysis does not necessarily imply causality. But this situation is different when we consider time series data. In time series data, the situation is different. As suggested by Gary Coop, time does not run backwards. That is, if event A has happened before event B, if event A happened before event B, then it is possible that A is causing B. A is causing B. However, it is not possible that B is causing A. In other words, events in the past can cause events to happen today. Future events cannot. So if event A happens before event B, then it is possible that A causes B, but B cannot cause A. That is, events in the past can cause events that is happening today, but events happening today cannot cause an event that has already occurred in the past. And this is roughly the idea behind Granger causality test. This is roughly the idea behind Granger causality test. Now, before explaining the procedure, let us consider a definition of what is Granger causality test. It was introduced in 1969. Now, as a definition, a variable yt is set to a variable xt is set to Granger cos yt. A variable xt is set to Granger cos yt if yt can be predicted with a greater accuracy by using past values of xt variable than not using such past values, all other terms remaining constant. A variable xt is set to Granger cos yt if yt can be predicted with greater accuracy by using past values of xt variable than not using such past values. Stated differently, x is set to Granger cos y if y can be better predicted using the history of both x and y than it can be by using the history of y alone. That is, x is set to Granger cos y if y can be better predicted using the history of both x and y than it can be by using history of y alone. That is the definition of Granger causality. Granger causality is actually a misnomer in the sense that it is not synonymous with correlation. And there is also considerable disagreement among econometricians regarding causality. Anyway, these are philosophical issues. We will not discuss such philosophical issues here. Now let us consider an example to see what is meant by Granger causality test. Now consider two variables xt and yt and consider a VAR model. We will explain VAR in the next session in detail. Now yt is equal to a1 plus sigma beta I xt minus I is equal to 1 to n plus sigma gamma I y t minus j is equal to 1 to m plus e1 t. xt is equal to a2 plus sigma theta I x t minus I is equal to 1 to n plus sigma delta j y t minus j plus e2 t. J is equal to 1 to m. Now, this e1t and e2t are unrelated white noise error terms. What this equation says is yt depends on the past values of x and also the past values of y. Xt depends on the past values of x and also the past values of y. Now, to test Granger causality, we consider the steps involved in testing Granger causality. The first step is we consider four cases. One is the logged values of x in the first equation is statistically different from 0 as a group. Logged values of x, that is xt minus I as a group is statistically different from 0 in the first equation, and the logged values of y is statistically not different from 0 as a group. Then we will say that xt is causing yt. This is different from 0 as a group, this is not. Then a second possibility is logged values of y is statistically different from 0 as a group in the second equation, and lagged values of x not statistically different from 0, is not statistically different from 0 in the first equation, then we will say that yt causes xt. Then lagged values of x is statistically different from 0 in the first. Lagged values of y is statistically different from 0 in the next. Then xt causes yt and yt causes xt. Then lagged values of xt is not statistically different from 0 as a group in the first equation. Lagged values of yt not statistically different from 0 in the second equation. Then there is no causality. There is no causality. These are the 4 possible cases. In the first, there is unidirectional causality from xt to yt. Second, unidirectional causality from yt to xt. In the third, bidirectional causality between xt and yt. And in the fourth case, there is no causality. Now let us see what are the steps in testing it. Now the first step is you consider the first equation. First equation only. Then the first step is regress yt on lagged values of yt. Regress yt on lagged values of yt alone. But do not include lagged values of xt. And obtain RSS from this model. Call this RSS restricted. It is RSS restricted because the lagged values of xt is not included in the regression. Then the second step is include lagged values of xt also in the equation in addition to lagged values of yt. Obtain RSS and call this RSS unrestricted. So yt on yt minus I x t minus I. Call this RSS unrestricted. Now we set the hypothesis. Our null hypothesis is H0 beta I is equal to 0. That is, xt does not Granger cause yt. That is, sigma beta I is equal to 0. Tested against H1, beta I not equal to 0. We are considering only the first equation. Remember that. Second equation will be considered later. Now we calculate, that is the third step. The fourth step is calculate f as is equal to RSS restricted minus RSS unrestricted divided by em all divided by RSS unrestricted divided by n minus k. And if the restrictions are valid means xt does not Granger cause y, this RSS will be much higher than this RSS. So that you will get a large f value. So that if f is greater than f alpha, reject H0. Reject H0 means xt Granger causes yt. Now here, this m is number of lagged terms in x. M is number of lagged terms. And k is number of parameters in the unrestricted regression. N is the sample size. So if f is greater than f alpha, reject H0, we will conclude that xt Granger causes yt. Now we repeat the same procedure for the second equation also. That is xt on lagged values of xt only. then xt on lagged values of xt and yt. Null hypothesis is delta j is equal to 0 versus delta j not equal to 0. Formulate f and take a decision. So in some cases xt Granger causes yt, yt Granger causes xt, or there will be bidirectional causality between xt and yt, and in some cases there will be no causality at all. These are the possible results. Now, this is Granger causality. So xt, yt, and take the lagged values, formulate the Granger causality. Now let me consider a very important point in the context of Granger causality tests. The point is, to implement Granger causality test, it is necessary that xt and yt are stationary. To implement Granger causality test, it is necessary that xt and yt are stationary. If xt and yt are not stationary, you cannot implement Granger causality test. That is a very important requirement in the Granger causality test. xt and yt should be stationary. And if they are not stationary, you should make it stationary. That is one point. The second point is, if xt and yt are not stationary, but suppose that they are non-stationary, but suppose also that they are co-integrated. So xt and yt are I1, but co-integrated. Co-integration is the concept which we have analyzed in the last class. That is, a linear combination of xt and yt is I0. Then in such a case, we test for co-integration and we reparameterize the model as EC, error correction model, or specifically VEC, ECM or VECM of the form delta yt is equal to alpha 1 plus alpha 2 delta yt minus 1 plus etc. alpha p delta yt minus p plus beta 1 delta x t minus 1 plus etc. beta q delta x t minus q plus lambda e t minus 1 plus vt. And et minus 1 is the lagged residual from co-integrating regression. And how to reparameterize a model into ECM, etc., will be considered in the next session when we study VAR and VECM in detail. Now, for the time being, just imagine that this is the ECM is the reparameterization of the original model, where we take a delta yt minus 1, yt minus p, xt minus 1, xt minus q, etc. And also the part et minus 1, that is et minus 1 shows equilibrium error as we have discussed in the last class, and lambda is the proportion of this error corrected in each period. Now, there are two sources of causation on y. One is two sources of causation. One is lagged values of xt. Lagged values of xt. And the second one is lagged values of co-integrating vector. Lagged values of co-integrating vector. In the standard Granger causality test, this term will not be there. This term will not be there because in the standard there is only these terms. So yt is caused by lagged values of xt and also the co-integrating vector. Now in Granger and Lin in 1995 has shown that the conventional Granger causality test is not valid if two variables are integrated or two variables are non-stationary or integrated. In 1995, Granger and Lin has shown that the conventional Granger causality test is not valid if two variables are integrated because two integrated variables cannot cause each other unless they are co-integrated. Two non-stationary variables cannot cause each other unless they are co-integrated. So if there is co-integration, we reparameterize a var. Actually, this is an example of a var that we will see in the next session. And this is the reparameterization of var. Actually, this is one equation, and if we write for yt, xt, zdt, etc., we have VECM, vector error correction model. And var and VECM are extensions of what we have seen as ARDL model, autoregressive distributed lag model, and ECM, error correction model. ECM is nothing but the reparameterization of ARDL, just like that. VECM is reparameterization of var, and we will see how var is reparameterized into VECM later. So if two variables are integrated, non-stationary, then Granger causality test is not valid because two integrated variables cannot cause each other unless they are co-integrated. So if two variables are co-integrated, we reparameterize var into VECM like this, and this is the co-integrating type. And as we have discussed in the last class, all the variables delta x, et minus 1, everything is stationary. There is no spurious regression problem here as we are considering only stationary variables. Now the H0 is beta 1, beta 2, etc. beta q equal to lambda equal to 0. And the null hypothesis is rejected if and only if these coefficients are non-zero or lambda not equal to 0. In the conventional Granger causality test, this term is not there. We reject H0 if beta 1, beta 2, etc. beta q equal to 0. But now we have to ensure that beta 1, beta 2, etc. beta q and also lambda equal to 0. And even if these beta coefficients are equal to 0, but lambda not equal to 0, but lambda we can, even if beta coefficients are 0, but lambda not equal to 0, we can reject H0. Suppose that these are all equal to 0. This is not equal to 0. Again we can reject H0. But in the conventional Granger causality test, if beta 1, beta 2, etc. beta q is equal to 0, we reject H0. That is the difference. Now, the steps are, if this is our framework, then the step is estimate this equation by OLS. estimate by OLS and obtain RSS. Call this RSS unrestricted. Then again re-estimate dropping lagged values of X and the EC term. Obtain RSS restricted. Then use the F-test. And this is the procedure. Now the question is how to implement all these things. If you are using eViews, the software eViews, then you have two possibilities. One is there is an option to estimate Granger causality. And when we implement Granger causality, remember that lag length is very crucial. So lag should be selected very carefully. And for lag selection, you use lag selection criteria like Agege information criteria, Skawar's information criteria, Hannenkin criteria, etc. Because causality is highly sensitive to the number of lags. For some lags, it will be significant. For other lags, it will not. So if XT and YT are stationary, you can simply use this Granger causality test, no problem. But if XT and YT also ZT, many variables, all are I1, integrated of order, etc., but co-integrated. Then we run VECM, Vector Error Correction Model. Once you estimate VECM, there is an option for Granger causality block exogenity test. In eViews. So this should be used if these variables are non-stationary. Use Granger causality block exogenity test, because Granger causality test is not valid if variables are non-stationary. One procedure is to make it stationary, then you will get only a short-run relation. The other one is establish co-integration. If they are co-integrated, that is lambda not equal to 0, then you can reformulate the VAR into VECM. Then after running the regression, you can use the Granger causality block exogenity test for a Granger causality test. And more about this we will discuss after considering VAR models. That is our next concern.